up, we have Ying Shi from NASA Goddard Space Flight Center, Enhanced Software Defects Classification with NLP. Ying, are you online?
Yeah, I'm on. Let me see if I can share. Give me a minute.
Sure, take your time, thanks.
So working or?
Your slides. Try sharing. Okay, now it came up. Can you go to presentation mode, please?
Yeah, okay. Let's see. So this works?
Use slideshow on. Yeah, got it. Thank you.
Okay, cool. Yeah. All right. So I'll drive from my side. Okay, good afternoon. My name is Ying Shi from NASA Goddard Safety and Mission Assurance Team. So my research background is empirical software engineering, which is used to use some empirical method like experiment, case studies, and data analysis to investigate and improve the practice process and therefore the quality of the software development and product. So I'm glad here today to present the current studies with all of you. Software defect data is one of the major data that we care about, but assessing defect data are not as straightforward as we thought. What we typically observe directly are the discrepancy and anomalies. What we document are called problem report or issue report. So the project, I believe, are required to document all the problem issues they found through either review, inspection, and testing. But not all the problem issues have defect. So over the years, we have collected tons of such problem issue data for a space project. So my interest is to find out what are the real defects and what kind of mistake we usually made or we repeatedly made, and what kind of surprise we encountered in the operational phase. Is that something that we saw before on ground testing, or some totally new behaviors? Or is there any ways that we can detect them early to reduce the development costs and fix them before launch? So, but manually process those tons of records are time consuming and sometimes need expert judgments. And so we're now thinking of whether we can utilize the latest large language model for text processing. A little bit outline of this presentation. I give you a brief introduction of the current status of our data collection process, and then how we want to classify a software defect using NLP. And we applied the current model to CFS, which is open source. And I would like to share with you some preliminary results and the directions that we're still working on. All right, many people probably see the chart before showing the exponentially growing of the NASA software in terms of the size, the lines of code, especially you can see for the deep space missions and those explorer missions, like the Mars missions, we see the size actually increase largely. And with the current increasing of the flight software complexity, and you hear about today the trending of adding more onboard autonomy and data processing, and think the trend will be continuing, which means that we have more reviews, inspection, testing that can be done. And then associated with that is the growing size of our problem issue report. So as I mentioned before, one of the empirical software engineering study areas is a defect study. So for example, those are questions we'd like to address in our studies, and how, for example, how can we use those discrepancy anomaly that we discovered to improve the overall quality and the reliability across the board? What are those discrepancy anomalies telling us about our design philosophy, those coding methods, the programmer's biases and some common parameters and cross-module dependence, all this type of the patterns that we see. And how can we discover them and address them early to be more effective? So in order to address those type of questions, we first need to consider a classification scheme for the existing anomaly discrepancy information that can help us distinguish between different type of issues and different type of the defects. So let's look at what kind of data we have already collected. So we usually use a discrepancy report for the issues we found during development. So either through review or inspection or testing, you probably have different terminologies used in your project or organizations. So we have seen that project using problem report, PR, problem failure report, PFR, the PRACAS, to document those discrepancy reports. And those are the issues found prior to launch and operation. So for on-orbit operational phase, so we call it anomaly report. So for instance, Goddard, we use a SwRI system, spacecraft on-orbit anomaly reporting system, to document those anomalies. We have collected over 9,000 flight segment anomalies over the years, and JPL, they have their ISA reporting system, instant surprise and anomaly. And for the discrepancy report, you probably see people using, as easy as Excel, and then the Jira system, Conference, and the GitHub, all kinds of different repositories to document those discrepancy report. And many of the systems were developed not really for the software anomaly documentation. For example, our source system in Goddard. So it's a hardware-based system, so it's not adequately address software failure behavior, and there's no place for document detailed the software defect characteristics. The data entry usually just include some problem descriptions, the date and time, the corrective actions, and the root cause. And a lot of cases, the root cause are not really identified. So, and of course, there is no breakdown of those types of defect. So this slide, it's just to introduce a straightforward, first a level of classifications for development phase discrepancy report. We could classify those issues to defect or bugs, which has a real incorrect implementations, like incorrect requirements, design implementations. Or we could have the enhancement features and not really defects, but the new features to be added to the next build. Or there's some questions with some unknown behaviors we don't understand, and could be as simple as cosmetic issues like documentation errors. And for the operational anomaly report, there could be the real failures or some unknown but benign behavior, sometimes are called idiosyncrasies. And we need a second level of breakdown of the defects. So there are many different classification schemes in literature over the past few years. We referenced many existing classification, and in combining with some real flight software actual failures, here I'll suggest the breakdowns. But this is only one way to break down the defects, and you could define your own category for a specific study purpose. And you can see that it's still kind of high level breakdown. So either the algorithm, the parameter, command script, your interface, your timing issue, your hardware issue. And there's a very interesting category here is sometimes with a lot of cases is missing, like missing stuff, missing scenario, missing a condition, missing a state, missing a requirement, missing parameters. A few JPL projects adopted this breakdown and introduced it in their tracking system. So that's great. So our objective is to categorize issues and defects. So let's recap what we have now. We have tons of historical issue data, but in different repositories and not characterized. And all this records in plain English language. Lots of acronym and project-specific terminologies are used. The development team has been dismissed and move on to new project. It's hard to reach back and explain or get some clarification if we have difficulty in understanding the text in the write-up. So one way is to propose using a unified repository with predefined category for everyone to use. We introduced this idea, but many centers and projects prefer to continue their existing system rather than adopt a new system. We understand their concern and hesitations. And anyway, it will take a few years to collect the data from the new system. And on the other hand, we have already has tons of categorized historical data that need to be studied anyway. So another more effective way is maybe try to utilize NLP and large language model to see if those new algorithms could help us categorize those data automatically. So since BERT was introduced in 2018, many variations of BERT has demoed a great capability of understanding and predicting text. So this is a typical data mining workflow. We need to do some pre-processing data, including clean up and tokenize those unrelated inputs, like images, like code, emails, and numbers, acronyms, and then we sampling the data. And here we have a limitation here is that we don't have a large set of training data that we can use. So we could manually categorize a few cases, and so we use a method called a few shot version of the BERT. And we reached out to, and it's currently collaborating with Dr. Filippo from University of Barry, who was also a University of Maryland and got a visiting scholar years ago. They have done a preliminary study comparing different BERT variants and try different sampling approach, and recommend us to use SetFit as SetFit model, which gives the highest F1 scores here. So this is directly from their papers, and they have done comparing different BERT variants, and SetFit actually gave the best F1 micro numbers here. And the beauty of SetFit is works for limited samples, which is in our case. And from the performance side, it's actually much faster than other traditional BERT and its variants. So the result actually is pretty similar to using a large set of training sets. But it's actually require a very precise examples. So which means that we need to correctly categorize the training data set to get the reasonable result. Okay, so we adopted his model and approach and applied it to the open source CFS issue report that available through GitHub. So this chart is showing the performance result. We actually randomly sampled 100 issues from each category. 50 is set to set aside for the training set, and the other half 50 for the test set. For the question category, we don't have many samples we can use, so we only test on 29 cases for questions. And the overall, accuracy is around 81%. But 80% of overall accuracy is probably not good enough. We don't want to miscategorize, for example, the actual defect to question or documentation and missed those defects, right? So there's a few ways to improve that. So we're continuing to collaborate with Dr. Filippo and fine-tuning these models. We actually tried a few different approach. I didn't got time to include the latest result here, but for example, we recently finished using a so-called zero-shot learning, which does not actually require any example. That will work perfectly for our second level of defect breakdown because we don't have any training data set yet, or we have only a few for each category. But unfortunately, the result are not as good as a few-shot model. And we're also trying to use more complex model like the GPT model, but the data restriction issue like the ITAR, even if GPT works better for CFS and GitHub project, we still cannot use it for actual project data. Or we're still trying to see if we can use a totally unsupervised learning without pre-identify the categories. We're working on that, but I'm not too optimistic about the result. So a more realistic ways to probably increase our training data. It sounds like that's a way we need to go with. We will need to manually classify a few data sets over there. And also the BERT is pre-trained the text on the generic language. So if we can include some NASA specific or space project specific language to the corporates to pre-train the data, that's probably a way to improve the understanding of the text. So those are the two approach that we're working on next step. And eventually our objective is to extend the current CFS issue label for the 4 category to as the next level. So to the proposed defect classification schema into our learning models. Put some reference here, and that's actually my last slide.